Hi, my name is Vinay, and in this video we will see the demonstration of an experiment which is an CMOS NAND gate using the DSCH software. So I've just opened my software. Okay, the experiment is from the VT University. So this is the experiment we will be performing. I'm sorry. Yeah. So we have to capture a schematic of two input CMOS NAND gate having a delay of the same of the CMOS simulator, which was the previous experiment, and we have to find the performance of it with all four possible inputs, and we have to tabulate the result and increase the drive time from 2x to 4x and tabulate the result. Okay, so let's do that. So I will demonstrate the working of it. The users can tabulate the result on their own. So I just open the folder from where I just load my schematic. So this is a schematic which is there in front of you. So I'm using a 45 nanometer technology. So that's why you can see that the width of the PMOS is 0.4 micrometer and the length is 50 nanometer, which is 45 nanometer. And the same is for the PMOS of this, and the same is for the NMOS transistor. So all four transistors are having equal sizes. I have loaded the output with 0.1 picofarad capacitance. Okay, so you can change the values of any one of you like. You can make it of your own by dragging dropping the symbols from the library and making the connection of them. You can change the width and the length from here. Okay, so this is what you can do. I can just remove this once. So if you want to perform a digital simulation, so you can run the simulation right over here in DSCH. So here you can see for when the both inputs are 1, then only the output is 0, otherwise it is 1. So that's how the functionality is of NAND gate. Okay, so this is a pattern based simulation. So if you see that this is only a digital simulation, but if you want to see an analog simulation of it, so you need to take the help of Winspice software. This is a third party spice simulator I'm making use of. To run the spice file, so I have to go to file, so generate spice file. Okay, so what he will do, he will apply a pulse input at both of the input switches which have been defined over here. So these are the two inputs, so he applies a pulse input. So the pulse width of the first one is 3 nanosecond and second one is 5 nanosecond with a rise time of 0.1 nanosecond. Okay, and the on periods are 1 and 2 nanosecond. So I can run it for only 10 nanosecond because 100 would be too large, and just a run Winspice. So there we see for 0 0 we get over here 0 0 you get 1, for 1 0 you get 1, and I think here, so for 0 0 this is how like you get it. Okay, now it's very difficult to understand because all the signals are multiplex. So what I do is I just make one of the input as VCC, so that we can just see one of them as inverter only. So I take a VD supply and connect to the one of the input. So now this time we will be only toggling the B signal. Okay, so you convert again to spice file and say run Winspice. So this time we can see that so when this is 1, so you can see the output goes 0. Okay, when this is 0, so this goes back to 1. So to measure the worst case delay, you can just zoom in the one of the block. Okay, and you can measure the delay from the 0.5 volt because that is the half of the supply. So this is, let's say this is 4 volt, and from here 4.5, so like 500 picosecond. So that is very equivalent to the inverter that we have made earlier. Okay, now if you want to apply a signal of your choice in a very specific format, so you can remove both of these two inputs and go to advanced tab of the symbol library, look for a voltage source and place two voltage sources next to each other and connect to the inputs and put a ground for them. So for this one I just go to pulse parameter, make the pulse width as maybe 10, the period as 20, rise time as 1, fall time as 1. And for this one, I can go make the pulse width as 20 and period as 40, and the rise and fall time are the same. Then you can again generate spice file, say run Winspice. We won't be able to see the entire thing because the width is set to simulation run only for 10 seconds. This time I'm making 100. So run Winspice. So there. So here you can see all the signals which are coming. So you can zoom up in one of the blocks and see what is happening. Now it's difficult to understand that okay, which nodes are where. The students might get confused. So to remove the confusion, you can just come back to DSCH and click View Electrical Net. So this time you will come to know that okay, which node is which one. So the fourth node is our output. So we'll look for V4, that is red in color. Okay, this time I just remove this. Yeah. So V4, this one is our output node, and 2 and 5 are our inputs. So 2 green, 5 is blue. So red one is our output. So we just zoom up in one of the blocks. So V4 is the red one. So we see that when both inputs are 1, 1, then the output goes blue. Okay. So you can zoom up in one of the blocks and measure the delays from the baseline of 0.54. So it's like 41.5 to 42 maybe. You can take it 42.1 maybe. Yeah. So that is your delay. Okay. So close to 100, like 0.4, 0.5 nanoseconds. Okay. So this is how you can just measure the delays, and you can tabulate in your results. Okay. So if you come back over here, now let's I just delete one of them and connect to a VDD so that we can just see them as an inverter, because that is the worst case delay of a NAND gate. And this time I just change the bit. Okay. Now if I quickly run again to just show you that this is functioning or not. Here this is functioning as an inverter, and the delays are, let's see, 62.5 to 63, around 500 picosecond. Okay. So here quickly I just change the width to 2x, that is 0.8. So I just copy this 0.8 micrometer and replace this in the widths of all the transistors. I'm not playing with the length. Yeah. And say go file, generate spice. So here we see that the delays have reduced. Okay, we zoom up in one of the blocks. So this time you see that it is okay, from here. So it's 62.5 to 62.8, almost like. So that is around 300 picoseconds. So the delays have reduced significantly. Okay. So that's our same way you can do it for 4x also. So for 4x it will be 1.2 micrometer. I just copy this so that it will be easier for me to paste it. And just say file, generate spice file, run. So there you are. So this is working fine, and we just zoom in one of the blocks. So from 0.5 to 62.5 to 62 point maybe here, and 500, 62.75 or maybe 75 something. So it's less than 300 definitely. It's like close to 220 something. So the delays have reduced significantly now. So that's how you can tabulate the result and put it in your reports. So this is, gentlemen, and CMOS based NAND circuit. So you can convert to the layout. In the next experiment we see the layout part of this. Thank you very much.